Hi there. Okay, so the second part of the thermal physics topic looks in particular at gases and modelling gases. Gases are in many ways more simple than the other types of materials, either phases or states, because they just consist of independent molecules or atoms that we can think of as particles. So, understand why they're the simplest states model, what assumptions do we make, understand how pressure can be explained, understand why temperature changes with change in volume and temperature, and introduce the concept of absolute temperature, which you probably are already familiar with. So this you're very familiar with again. The internal energy of a substance is a combination of kinetic energies in the first row and potential energies in the second row, with the total internal energy being the total kinetic and potential energy. In a gas, we forget about these. In an ideal gas, okay, we always forget about the intramolecular because that's chemistry, but in an intermolecular forces between particles, in an ideal gas, which is it's not a real gas, but it approximates to a real gas, we can forget about these forces as well. So as long as we're forgetting about those forces, then this energy doesn't exist. And the only kind of energy we have is kinetic energy. So any changes that we make to the kinetic energy, in terms of adding it or subtracting it, they will be changes made to the total internal energy. So temperature is a measurement of the average kinetic energy. That's worthwhile remembering. We'll come back to that later. Now, when we're talking about a kinetic energy, an ideal gas, then as I've said, there are certain assumptions that we make. We assume we have a very large number of particles. Everything in the gas laws that we're going to study is kind of based on statistics, and thermal physics as a whole is often known technically as statistical physics. Because it does rely on, rather than the behavior of any one particle, on the average behavior of many hundreds of thousands or millions of particles. So one of the assumptions is that we have a large number of particles. One of the other assumptions is that they are very small, or in fact technically have no size at all, which obviously isn't very realistic, but it's an assumption. And it's a reasonable assumption. And on average, if you look down back at here, the separation between particles, on average in a gas, is 10 to the minus 7 meters, whereas the average size of a gas particle is about 10 to the minus 10 meters. So, there's 3 orders of magnitude difference in there. So it's imagine if you had each particle was a ball about, 1 centimeter across, then there'd be 10 meters between the balls on average. So it's a reasonable assumption. Their motion is random, and we only care about the random motion, not about any sort of uniform motion like you might get if the gas was moving. The particles themselves can be assumed to be elastic balls, or rather that the collisions between them are elastic, and the collisions between them and the container are elastic. Just to remind you what that means, it means that not only is total energy conserved, which it must be, the kinetic energy is conserved. And as I've said before, there are no forces between the particles. Okay. In terms of what that actually means, in terms of what we can measure for a gas, what we call its macroscopic properties, the macroscopic properties of a gas basically are the pressure, by which we mean the pressure it exerts on the walls of a container, or if we put sort of a cube in here, the pressure that would be exerted on each face of the cube or any object. The volume that the gas occupies, which will generally be the volume of the container that it's in, although that volume could vary because you could have a fixed container like a box, or you could have a variable container like a balloon. The temperature of a gas as measured in Kelvin, and this is very, 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 very important. Earlier, when we were looking at change in temperature, it did not matter if you used Celsius or Kelvin. Here, it absolutely matters. You must use Kelvin. And the amount of gas is measured in moles. Okay, not just in number of particles, we use moles. And if we change any one of those, if we try to change the pressure by squeezing it, then we must change at least one of the others. If we introduce more gas, then at least one of those must change. Okay? And the relationship between them is all described in terms of a single equation, which we'll get to later. We've talked about pressure before, but it's worthwhile thinking about exactly where the pressure in a gas comes from. And it comes from the force of these particles hitting and rebounding. Okay, if we make the box bigger, that makes the area bigger, but if the amount of gas stays the same, then the force will stay the same, which will make the pressure less. But pressure equals force over area, which is just a restatement of Newton's second law. And the units of pressure, as we've seen before, are newtons per meter squared, or pascals, abbreviated to PA. So because there is a change in momentum, they have initial momentum, mv, and final momentum minus mv, and so the change in momentum is minus 2mv. You should remember that equation and that relationship from the previous unit. So the force, Newton's second law, is change in momentum over change in time, therefore pressure, big P, momentum, little p, big P pressure equals change in a force divided by area, so it's change in momentum divided by area times the time. So you have this equation relates the amount of gas, because the amount of gas is the m gives you the m in the momentum, and the temperature, because that gives you the v in momentum, because momentum equals mv, and the volume of gas, which is an area. So all of these, the amount of gas, the volume of a container, the volume of the gas, the temperature of the gas, and the amount of the gas are all contributors towards this equation to determine the pressure. Let's see what that means. Suppose we have a cylinder like this where we can move one face, but we keep the temperature constant. Now, this is actually more difficult than it sounds, because the only way we can squeeze this gas is by giving it force, and force carries energy, and therefore we're passing energy onto the container, and because it's a gas, Q equals U. If we increase Q, that means we increase U, and because U in a gas is just kinetic energy, that means we increase the kinetic energy, and that means the temperature. It's actually impossible to push on a gas without increasing the temperature. Well, how do we keep the temperature constant? Well, the answer there is to do it slowly, because this is not an isolated system. We can imagine that this cylinder is sitting in a room somewhere. So therefore, by doing it slowly, it will increase the temperature by minuscule amounts, but as it does so, that increase in temperature means that it conducts heat to its surroundings, so the actual temperature stays constant. Yet the effects of the reduced volume will still be observed in terms of pressure. Okay, so as long as the temperature is kept constant, if we decrease the volume, then the pressure will happen. Why will it happen? Because the particles are still moving with the same kinetic energy. They've all got the same temperature. Kinetic energy is the same. But now, because the box is smaller, they'll be hitting the sides more frequently. Therefore, the force will be greater. Okay? And delta T, the time between collisions, will be less. So therefore, the pressure must increase. In fact, we can draw a graph of that. We can draw, this is a different thing. This is keeping the volume constant. So imagine that same container, but we just have a fixed box, and we increase the temperature. As we increase the temperature, we give kinetic energy to the particles, so they move faster, so that reduces collision time and increases the force of the collisions, because P equals mv, and therefore greater temperature, greater pressure. It's a nice linear relationship. Don't forget, this is an ideal gas, and then one of the properties of an ideal gas is that no matter what the temperature is, it's a gas. It doesn't, at no point does it sublime or condense into a liquid or a solid, so it stays a gas. But here you can see that there is, and this is valid for most gases, a linear relationship. What gets a little bit dodgy is you reduce the temperature, but we can conjecture a reduction in temperature. If we draw the graph backwards, we will get to minus 273 degrees C. What does that mean? That means that if we theoretically could reduce the temperature to minus 273 degrees C, then there would be no movement of particles. Therefore, there would be no pressure, because there would be no collisions. And that is the basis of the Kelvin scale of temperature, which we have previously met. So with Kelvin, all we're doing is really just shifting the zero. We're shifting the zero to a logical place. We're shifting the zero to the temperature at which the movement of particles stops. You can't have negative movement, so therefore you can't have negative temperature. So, understand why gases are the simplest states model. Well, they are, because they don't have lots of complicated forces between them. In reality, they do have some, but we ignore those and call it an ideal gas. What are the assumptions? We assume that it's elastic collisions. We assume that they're very, very small or point-sized. We assume that the temperature is directly proportional to kinetic energy. We assume there's no forces between particles, and we assume there's lots of particles. Statistical physics. Understand how pressure exerted by a gas can be explained in terms of molecular motion. It's a force caused by a change in momentum. Okay, and then the force divided by area gives you the pressure. Understand why pressure changes with a change in volume and temperature. Well, if you change the volume, keeping the temperature same, then the time between collisions changes and therefore increases the pressure. If you change the temperature, keeping the volume in same, then the P equals mv, the velocity increases, therefore the increase in force, which increases the pressure. And understand the concept of absolute temperature, understand why it's based on the pressure of a fixed volume of gas. Because if temperature goes down, the velocity goes down until at some temperature the velocity will be zero, at which point the gases molecules will not be colliding with anything, at which point there will be no pressure. Just before I finish, that situation would never occur in reality, because once you start really cooling gases down, strange things happen due to quantum physics and uncertainty principle. But in classical physics, we can conjecture that temperature, and that temperature is minus 273.15 degrees Celsius or 0 Kelvin. Thank you very much.